Okay, the method of cross and uncross strings. So this is, I'd say, up there with the bizarre things in heat transfer that work, and I don't really know why. But the idea is as follows. So let's say we have a surface, and it looks like this. It's some weird surface. And then you have another surface down here. If you take a string, basically a line, and you connect the line from one extreme point of this to another. So what I mean is let's go for this line first, and then let's go from this line to this line. Okay, so that's step one. So and I think maybe there's some like kind of gray area about what the extreme point means, but I think for most geometries you're just looking at sort of where is the farthest thing that's seeing the other surface. So in that case it would be like way out here as I've drawn it. Okay, anyway, so you have these are the uncrossed strings, meaning these are lines that don't cross each other. Then you go back and you draw a second set of lines from these corners like this. And those are your crossed strings. So this method says, well, let me first give some labels here. So this up here is surface 2. This is surface 1. It's a bad one. This is surface 1. Let's call this point over here A. Let's call this B. This is C. This is D. So we have 4 points. This method, by the way, only works for 2D geometries, as far as I know. So this is a 2D system. You have these two surfaces that have this shape, and they extend infinitely out of the page. Okay, so what this method says is, again, sorry, let's do 1. So A1 F12 equals A2 F21, just the reciprocity. Both of those are equal to this parameter called W. Right? So W is going to be our length into page. So W times the summation of the length of the crossed strings minus summation of the length of the uncrossed divided by 2. So for this case, it would be equal to W times LAC plus LBD minus LAD plus LBC. Sorry, LBC. Did I get that? AC, BD, AD, AC divided by 2. That gives you the product of the area times the view factor.
That W is multiplying the entire
Yeah.
fraction on the other side.
Yeah.
Okay.
Thank you. Yep. So this is the first dimension, and then the second dimension is covered by W. So this is saying if I just compute the actual distance in space between points A and C, B and D, AD and BC, I know those lengths, I can compute the view factor, okay, regardless of the shape of the surface. John? It's a, okay, I'm guessing now, but it's not experimental. I actually am, say, like 90% confident that it is a property of geometry. It just arises from geometric concerns.
So it's always between 0 and 1?
It's always, so this will give you back a number which is the product of the area times the view factor. So if you wanted the number between 0 and 1, divide by the area.
I see, right.
Yeah.
Gotcha.
Yeah.
Okay, that makes sense.
So it's kind of like funny, and the thing that's even funnier about this is, let's say now I have some rectangle over here, and I take that rectangle and I move it over here. Okay, now I'm going to redraw this line like this. It still works. I don't know.
Does it have to follow the edge? Like, does it have to go vertical along?
I guess you'd want to say it's like a relatively thin obstruction like this. But yeah.
How you curve the line change the answer though?
Okay, yeah, so I didn't really curve it. You guys are nitpicking. It looks like this, right? Okay. It still works, but so as long as you can compute the length of these compound segment, it will still work. Okay, so this actually becomes a pretty powerful technique if you don't have others available to you as well. Okay, yeah.
Does this still work if, say, B and C are touching?
If B and if they're touching,
B and C are
oh.
coincident.
Oh, that's a good question. So what would happen? So you'd have LBC would go to 0 there.
BB might go to 0.
BD would just be the length of this. I actually don't know the answer to that. Yeah, I guess I wonder though if you, let's say the surface is like this, right? It's an arced surface. So does that mess it up? I don't know. I don't know.
Would DC be like a straight line length or like follow the edge along the surface?
That's another good question. I don't know. Yeah, Austin.
Can you add it, like, let's say you can do this, and let's say the bottom is like a parabola, you split it in half, like, because you couldn't draw like a line from the bottom shape like a parabola. Is it additive?
So you're saying if it looked like this, would you draw a line up and then a line down?
Yeah, like 2 segments.
I think if anything, it would have to follow along the path that exists. If it's a parabola, it'd have to follow along that parabolic path. But again, yeah, this might be, so there is an original publication that is referenced in the book that probably describes this in more detail. As far as I know, I don't know where that publication is, if it even exists anymore in any archive. So I haven't been able to track down the original publication on it, but if somebody had more attention than I did on this, they could probably do it. But in many of the simple cases, or the maybe like obvious cases where you have spatial separation between two surfaces, it works as shown here. Okay. So in the remaining time, I guess, today, let's talk about, so this is the complete set, right? Let's see, we went back, let's look at our list here. So we talked about inspection, the library, view factor integral, the rules, the method of strings, and then we didn't get to Monte Carlo. Monte Carlo is kind of its own topic, and we'll hopefully have a lecture on that towards the end, or maybe next time, I'll say next time. But this gives you like the tool set that you need now to be able to go through and do actual problems in this.